Welcome back, students. In this video segment, we will take a look at section 2.3, computing the values of trigonometric functions of acute angles. Unlike the title of the section is very, very short compared to section 2.2. So let's get started right away. In this section, we address something very that happens very commonly in physics, in calculus, and in general in STEM field math courses. We need to be able to access the values of the 6 trig functions for a specific list of special angles, and we need to be able to do this quickly and without the use of a graphing calculator or any kind of calculator. And it turns out that it's very easy to do this. There are several ways of doing it. In section 2.3, what we do is we use a little simple geometry to compute the values of the trig functions. So let's get started. What I've constructed for us is an equilateral triangle, and what I'd like to do is to make the equilateral triangle so each side has length 2. So each side has length 2. And if you remember from geometry, the sum of the angles in any triangle is 180 degrees. So since an equilateral triangle has angles that are also equal, each of those angles must be the total sum, 180 divided by 3, or 60. So each of the angles in an equilateral triangle are 60 degrees. Okay, now before I draw in that last angle up top, what I want to do is I want to slice this equilateral triangle in half by dropping a perpendicular bisector from the upper vertex down to the horizontal side. Okay, so what I'm going to do is I'm going to attempt that. Let's see if my service will allow me to do that today. Cool. Okay, so what I've done is I've dropped the perpendicular bisector from the upper vertex to the horizontal side. What that perpendicular bisector does is 2 things. It cuts the angle up top in the big equilateral triangle in half. So let's write that new angle as 30 degrees. The third angle in that little triangle on the right is got to be a 90-degree angle. So we're looking at a 30, 60, 90 triangle, and that perpendicular bisector also cut the bottom side in half. So this new side here has length 1, half of 2. Okay, so let me get rid of that side of length 2. And now we're looking at a 30, 60, 90 triangle. So on the lower right-hand side, or the right-hand portion of this cut in half equilateral triangle. So let's isolate that 30, 60, 90 triangle. Let's eliminate the right-hand version of that 30, 60, 90 triangle. So I'm going to attempt to do that with my eraser. Okay, here we go. Okay, I guess I could have shut the video off so you didn't have to watch me do all this erasing work. That's all right. All right. Now, if you remember the 30, 60, 90 triangle from geometry, you could skip this step of constructing it. The only thing left in the 30, 60, 90 triangle is the vertical side. And to get that, we use the Pythagorean theorem. We can call the vertical side, say, b. We do that. And the Pythagorean theorem says 1 squared plus b squared equals 2 squared. So 1 plus b squared equals 4. B squared equals 3. So b equals plus minus radical 3, but we're looking at the length of a triangle, or the side of a triangle. So b has to equal the square root of 3. The important thing is to get some of the values of these trig functions that we really need to be able to access quickly. We need a 30, 60, 90 triangle. We need the 30, 60, 90 triangle. So let me get rid of our computations here. And let's say put the side of length radical 3 up here. Sorry about my border collie in the background. Let's see. One time last semester or last session, one of my students was listening to a video at like 3 in the morning or something like that. It was real quiet, and then my dog came right up to the computer and just let out this huge bark at someone going by, and she said it scared the devil out of her. Anyway, so we'll try to keep the barking to a minimum here. All right, so that third side is side radical 3. The important thing is with this right triangle, then we're able to access a lot of information about the 6 trig functions. So I want to show you how to do that. There are better ways of doing this, so this is sort of a first attempt. We need to be able to access the sine, the cosine, the tangent, the values of all the 6 trig functions of, in particular, 30 degrees and 60 degrees. And this triangle allows us to do that right away. So for example, if I want the sine of 60 degrees, that's real easy to get from this triangle, because remember, we have that device, SOHCAHTOA, that allows us that if we have a right triangle right away, we can just access the 6 trig functions. Sine is opposite 60 is radical 3, and hypotenuse is 2. Cosine of 60 is adjacent over hypotenuse. The tangent is opposite over adjacent. So the tangent of 60 is radical 3 over 1, or radical 3. Now you could either use the triangle, or you can just remember that the other 3 trig functions are simply the reciprocals of the first 3 in order. So the cosecant is 1 over the sine. The cosecant of 60 is 1 over the sine of 60. The secant of 60 is 1 over the cosine, and the cotangent of 60 is 1 over the tangent of 60. Okay. We could have done the same thing with 30 degrees. I'll just do one of the trig functions. Let's say the sine of 30 degrees is opposite 30. Opposite 30 is 1. And the hypotenuse is 2. So how else could I, while I'm doing that, how else could I have done the sine of 30? Just kind of a reminder. The sine of 30. I could have used the identities from the last section that says that cofunctions of complementary angles are equal. So the sine and cosine are cofunctions, and the complementary angle to 30 is 90 minus 30, or 60. And the cosine of 60 I've just found above. The cosine of 60 was 1/2. So there are multiple ways of getting at the values of the trig functions. This is okay. This method's okay, but it's not real efficient. It would be nice if we could find the values of the 6 trig functions much more quickly than this, of say the secant of 60, and come up with it as being 2 almost immediately, and rather than drawing a triangle, constructing a triangle, etc., etc. So I'm going to show you how to do that. Your author doesn't show you a nice little compact table for this. He sort of starts it, but I have a nice compact table that I didn't make up the table. It's called the chart of special values that I'll give you in a few minutes. Before we do that, let's take a look at finding some of the values of the trig functions at, say, 45 degrees. So to do that, here's a 45, 45, 90 triangle. So of course it has a 90-degree angle. Let's say the 2 legs have length 1. Okay, what does the Pythagorean theorem leave for the hypotenuse? Did you think of it? Square root of 2. Okay, you can always stop the video and compute these items or think about these items a little bit. You don't have to let the video keep going. I also discovered on YouTube that you can slow down the video. In the lower part of the screen, you can click on something that will slow my talking down. I can't imagine you can also speed it up. I can't imagine you wanting to speed things up. But anyways, so we have a 45, 45, 90 triangle. The sum of the angles has to be 180 again in any triangle. So the two non-right angles have to add up to half of 180, which is 90. So each of them needs to be 45, half of 90. All this is from geometry, sort of a quick reminder. So from this right triangle, we can find the values of all 6 of the trig functions for 45 degrees. The sine of 45, the cosine of 45, the tangent of 45 degrees, the cosecant of 45, the secant of 45, and the cotangent of 45 degrees. Okay, so I'm listing all the trig functions in order just like we always do. Same order every time. The sine, remember SOHCAHTOA says the sine is opposite over hypotenuse, so 1 over the square root of 2. If we consider the angle in the lower left-hand corner, so there's the angle, because the other one's also 45 in the upper corner. So just to let you know which one I'm using for SOHCAHTOA, the cosine is adjacent, 1 over radical 2. The tangent is opposite over adjacent, so the tangent is 1. Tangent is 1. It's a funny looking one. If you rationalize the denominator for 1 over the radical 2, you get radical 2 over 2. Okay, remember, you should be able to deal with the trig function values either with rationalized denominators or with radicals in the denominator. The cosecant, the secant, and cotangent are the reciprocals of the first 3 trig functions in order. So their value, their values are radical 2, and 1 over 1 is 1. So the cotangent of 45 degrees is 1. So can you tell me what the sine of pi over 4 is? Can you compute the sine of pi over 4 very quickly? Okay, the key is that pi over 4 is the same thing as 45 degrees, which at this point should be pretty much automatic to you that pi over 4 is 45 degrees. If not, you might want to review the angles, special angles measured in radians. The sine of pi over 4 is the same thing as the sine of 45 degrees. It's radical 2 over 2. What if I want the secant of pi over 3? Just an oddball number. Secant of pi over 3. Well, we would look up at, well, actually, we would realize that pi over 3 is how many degrees? Pi over 3 is 60 degrees. Just as a really quick reminder, if you take pi over, if you don't remember that pi over 3, and you multiply by 180 degrees over pi, you get 60 degrees. So this is kind of a brief reminder in case you didn't remember that pi over 3 was 60 degrees. It'll become automatic. We deal with these angles, same angles all the time, but you can really, really quickly convert from one system to another so that we get the secant of 60 degrees, that's secant of pi over 3. We look up at our computation and says that the secant of 60 degrees is 2. Okay, these are everyday kind of computations that happen in calculus, physics, wherever we use this stuff. So 2, secant of pi over 3 is 2. Okay, now what I'd like to do is share with you an easy way, a much easier way, a much quicker way of accessing the values of the 6 trig functions for special angles. I'm going to include angles that we haven't seen yet for the trig functions. The trig functions are computed for acute angles now, which are angles between 0 and 90, not including 0 and not including 90. In the next section, we're going to include 0 and 90, or 0 and pi over 2 in radians. So I'm going to include them in this special chart that I'm going to construct, and we can kind of just accept that their values are what they are until we get to section 2.4. Okay, so I'm going to set up a really nice chart of special angles here. I think it's real nice. So I need a chart. So I'm going to construct a little chart here. If I can. And I need to divide up the chart into 3 segments. So for one segment, I use a nice line. For the other segment, I get a crooked line. That's all right. And then in this chart, I'm going to write 2 words. I'm going to write sine, and I'm going to write cosine. And above that, I'm going to write the word angle. Okay. And I'm going to divide up the chart into different segments. I'm going to put the angle 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. These are called special angles. These are called special angles. Those same angles we can also consider in radians. So in radians, they would be 0. Do you remember what this one should be? What is 30 degrees? It should be pi over 6, pi over 4 for 45, pi over 3 for 60, and pi over 2 for 90. Now, this chart that I'm going to construct has, let's see, looks like 10 items, 10 quantities. We're going to be able to compute a whole lot more than that with this one little chart. Okay, so here's how we do this. To construct the numbers in the chart is very simple. All we need to be able to do is to count from 0 to 4. Okay, essentially. So I'm going to write 0, 1, 2, 3, and 4. Then I'm going to count from 4 back to 0. 4, 3, 2, 1, and 0. We're not done. I'm going to take the square root of each of the numbers. I'm going to write the square root symbol over each of the numbers. So far, this is the simplest thing in the world to do. Square root, square root, square root, square root. And finally, I'm going to divide each entry by 2. 2, 2, divided by 2. Okay. So I claim that we can get 60 pieces of information from this chart that only has 10 things in it. And here's how. How many trig functions are there? There are 6. How many angles are here? There are 5. So I should be able to compute 6 times 5, or 30 things. Well, that's half of 60. How about the other 30? Well, half of the 60 items that the trig functions of these angles are in degrees, or using angles in degrees, and half of them are in radians. I claim 60 things can be found here. Now, you're thinking, well, you only have 2 trig functions here. What about tangent, cosine, cotangent, etc.? Well, here's some examples. From this chart, how do I figure out, say, the cosine of 0 degrees? Even though we're not allowed to use non-acute angles in this section. Suppose I want the cosine of 0 degrees. Well, you look up the column with 0, you look up the row with cosine. Cosine of 0 is radical 4 over 2. Well, radical 4 over 2, just as kind of a reality check, isn't, we don't write it as radical 4 over 2. The square root of 4 is 2. 2 over 2 is 1. Okay, so the cosine of 0 is 1. Cosine of 0 degrees is 1. Now then, another example, before we get something besides sine or cosine, what about the sine of pi over 4? Sine of pi over 4. Well, look at pi over 4. The column where pi over 4 is right in the middle column of the angles, and the sine row is the first row of sine or cosine, so you get radical 2 over 2. So what about something that's not on here? What about something like the tangent of pi over 3? Clearly, tangent isn't on here, but we have fundamental identities, which you should be getting really familiar with, especially after that long section 2.2. The tangent is sine over cosine. So the tangent of pi over 3 is sine over cosine of pi over 3. Sine of pi over 3 over cosine of pi over 3. You look up pi over 3. The sine of pi over 3. What's the sine of pi over 3 according to this? Think about it for a second. Sine of pi over 3. Pi over 3 column, sine row. We get radical 3 over 2. And the cosine of pi over 3 is radical 1 over 2. And a little reality check, we don't write radical 1. The square root of 1 is simply 1. So the radical 1 over 2 is 1/2. Okay, so this is sine of pi over 3 over cosine of pi over 3. Cosine of pi over 3 is 1/2. If you invert and multiply, the 2's cancel. You get radical 3. This is the power of this chart, is that we can access a whole lot of information just by looking at 6 items on this, or rather 10 items on the chart. We can get 60 things. Okay, so suppose I want another one. Suppose I want something like the secant of pi over 2. Secant of pi over 2. Okay, so the secant of pi over 2, secant's not on there, only sine and cosine are on the chart. So we remember that secant is 1 over the cosine. The fundamental identities, absolutely important, absolutely essential to memorize. And from the chart above, the cosine of pi over 2 is right there. The cosine of pi over 2 is radical 0 over 2. Reality check, the square root of 0 is 0. Okay, so we would write the cosine of pi over 2 is 0. Back to our example, the cosine of pi over 2 is 0, and 1 over 0 is undefined. So we get something strange. Undefined. Not all of the trig functions are defined for all of the special angles, the 5 special angles. In particular, the secant of pi over 2 is undefined. Okay, that doesn't happen really in section 2.3. So again, I'm letting a few things from section 2.4 out in this section. Okay, so let's take a look at a specific example. Suppose, for example, I want to find the exact value. Find the exact value of each. Couple of parts to this example. Part A, suppose I want the exact value of the, let's say something like the sine of 30 degrees times the tangent of 60 degrees. It's funny looking, 60 degrees, tangent of 60 degrees. Well, chart of special values. The sine of 30 degrees is, look up 30 degrees, look up sine, it's radical 1 over 2, which is 1/2. So the sine of 30 degrees is 1/2. The tangent of 60 degrees, well, tangent is not there. I claim that the tangent of 60 degrees is on your screen right now. I claim that the tangent of 60 degrees is on your screen right now without having to do anything. Without having to do anything at all. So where is it? I'm going to give you a great big hint. great big hint. I'm going to highlight where it is. Let's see if I can. There it is in red. See, pi over 3 is 60 degrees. Pi over 3 is in fact 60 degrees. So we have a bonus with that computation that we did earlier. The tangent of pi over 3 is the same thing as the tangent of 60 degrees. So the tangent of 60 degrees is radical 3. These computations, all these computations I'm doing are absolutely common in physics and calculus, which is where most people who take trig are ultimately going. So the tangent of 60 degrees is pi over 3. I'm sorry, tangent of 60 degrees. 60 degrees is pi over 3. So the tangent of 60 degrees is radical 3, which we can write as 1/2 times radical 3 over 1 to get radical 3 over 2. Okay. Okay, so the second example, and then we'll move on. B. Suppose I want something like 4 plus tangent squared pi over 3. Pi over, yeah, why not? Pi over 3. 4 plus tangent squared pi over 3. Okay, well, this is 4 plus, I do believe we have the tangent of pi over 3 again. It's radical 3, so 4 plus radical 3 squared, which is 4 plus 3, which is 7. Okay. Okay. Well, I mentioned this was going to be a short section. We have one other thing to do. A couple of cautionary notes with this last thing, though, is it involves using the calculator to estimate values of the trig functions. Be very careful on your homework, and even more, maybe even more careful on your exams, that when you're asked to find the exact value of something, it means essentially do not use the calculator, any kind of calculator, to do it. For example, or specifically, if I wanted the exact value of the cosine of pi over 6, go to a chart. Cosine of pi over 6 would be radical 3 over 2. Now, if you used your calculator to estimate radical 3 over 2 and you wrote that down, you would lose all the credit for that problem. Be very, very careful. Fair warning, when you're asked for exact values, it means exact values, just that. And it means essentially don't use your graphing calculator. There'll be times often when we use the calculator to compute stuff. Let's take a look at how we would use the calculator to compute some values. So using a calculator. Suppose I want to compute the sine of 30 degrees. Okay, well, it's equal to 1/2. It's on the chart of special values. But suppose I want to use the calculator to find the value or estimate the value of the sine of 30 degrees. The first thing we need to do is make sure the calculator is in the correct mode for the angle. That is, that it's in the degree mode. Sorry about the little fumble there. So first, you must do this first. Make sure the calculator is in degree mode. Make sure the calculator is in degree mode. All you do is you turn your calculator on, push mode, and look which of the two possibilities for angle types is highlighted. On my calculator, I have it highlighted under, or rather radians is highlighted. So I would put the cursor down so it's flashing over degrees, and I push enter, and now the calculator is ready to compute the trig function values in degrees. I would push second mode, second quit, to get out of there, and all you have to do is push sine 30. You don't have to put degree symbols. Your calculator is already interpreting the angle as degrees. Close the parentheses and push enter. And what you should get is 0.5. Okay. So suppose right after that, I want to compute the cosine of pi over 3. Cosine of pi over 3. All right. So put your calculator in the radian mode. How do I know it's in radians? If you said because of the pi, you are absolutely wrong. Because an angle has pi in it doesn't make it radians. What makes pi over 3 radians? Think about it. This is going to be a potentially point value expensive mistake on a test. Okay, so be very careful. What makes pi over 3 a radian? It's not the pi. It's the fact that it's missing a degree symbol. Okay, we can have pi degrees. Okay, so it's a radian. So you got to put your calculator in the radian mode. Okay, so radian mode. Go back to your mode just for practice. Go back to mode. Get the cursor highlighted over, flashing over radians. Push enter. Then all you do is you push cosine pi divided by 3, close parentheses, push enter. The cosine of pi over 3 is also 0.5. Okay, cosine of pi over 3 is 0.5. Why is it that the sine of 30 and the cosine of pi over 3 is 0.5 are both equal to 0.5? Why is that true? Well, here's the reason. Sine of 30, use the complementary angle theorem, is the cosine, so cofunctions of complementary angles, 90 minus 30. So it's the cosine of 60, and 60 is pi over 3. So the sine of 30 is the cosine of pi over 3. So it's not just a strange coincidence that sine of 30 is cosine of pi over 3. It's because of the relationship between sine and cosine. Okay. So suppose I wanted something that's not on the chart. Suppose I wanted something like the cosecant of 1 degree. Okay. Now on your calculator, you have access to only 3 of the 6 trig functions. 3. On the calculator, you have 3 trig functions only. The calculator, oh my goodness, my L looks horrible. Calculator, T looks even worse, has sine, cosine, and tangent. It does not have, these are supposed to be buttons, it does not have cosecant, secant, and cotangent. It looks like it does, because the second functions on the calculator look like this. They look like sine -1 power, cosine -1 power, tangent -1 power. And that -1 power doesn't mean what you might think it means. The -1 power in this notation is not reciprocal, is not 1 over. This is not reciprocal. It's for something later. Okay, so it's not 1 over sine. But if it were 1 over sine, then that would be cosecant. So the calculator doesn't have access to, or doesn't give you access to the cosecant, which is 1 over sine, secant, and cotangent. So what do? It's not difficult. It becomes even easier with more practice. The cosecant of 1 degrees is 1 over the sine of 1 degrees. Fundamental identities. In your calculator, you would push 1 divided by the sine of 1 degrees, and then enter. Close the parentheses and then enter. So it would probably give you the wrong answer right now if you were playing with the calculator as I was doing this, because in our calculator right now, the mode should be in the radian mode. it would give you the wrong answer. So make sure your calculator is in the correct mode. Make sure the calculator is in the correct mode. Okay, before you start computing values of the trig functions. Degree mode. Degree mode. Okay, so once we do that, once we get it into the degree mode, we push 1 divided by sine 1. Don't have to enter the symbol for degrees. The calculator already knows. And you get, about, let's say, 57.298 so approximately, just rounding to 4 decimal places. Okay. One more example. Suppose I wanted the cotangent of 4. It's very common for students to make a mistake on this. Okay, this is not the cotangent of 4 degrees. Why not? Because there's no degree symbol on the 4. This is the cotangent of 4 radians. So you got to put your calculator back in the radian mode. Back in the radian mode. And once your calculator is back in the radian mode, the cotangent of 4 is 1 divided by the tangent of 4, fundamental identity. Your calculator, you compute 1 divided by tangent 4, and it should work out. I'm lagging a little behind in my calculator, so I gotta change it to radians. So 1 divided by tangent 4, close parentheses, is about 0.8637 to 4 decimal place. So this is approximately 0.8637. Okay, as a final note for this section, I'm basically repeating something that I've noted over, I've taught this course almost every semester for 30 years. And it's very common for students to not change or have the calculator in the wrong mode, and it will destroy your solution. So make sure when you're dealing with radians, your calculator is in the radian mode. If you're dealing with degrees, it's in the degree mode. And the second thing to note is if you're asked for exact values, do not reach for your calculator. Don't do it. Don't do it. Don't do it. It's very common for students to give decimal values when I'm asking for exact values, and you will get no credit for it. I very specifically want what I'm asking for, okay? The sciences are about precision and not giving or not quickly giving the wrong units of things or considering things in the wrong units, okay? Devastating things happen in the sciences when you're sloppy with units. If you want an example of that, look up the history on the Hubble telescope. You can get a nice snapshot of why obsession to detail in the sciences is absolutely critical. It costs a lot of money to make a tiny little error, what seems like a tiny little error in units with the Hubble telescope. Maybe you want to look that up, and I'm not going to test you on it. It's kind of interesting. So that's it. That's it for this section. We just finished up section 2.3, and as usual, I am looking forward to talking with you all again soon.